All right, in this video, we're going to cover section 6.3 on maximum and minimum problems. So these are applied problems for the most part that use partial derivatives. So the objectives here are to find relative extrema, meaning maxes and mins, of a function of two variables, and then to solve applied problems by finding the minimum or maximum of a function of two variables. All right, so the definition of a relative maximum and relative minimum. A function f of two variables has a relative maximum at the ordered pair AB if the function value of xy is less than or equal to the function value at AB for all points xy in a region containing AB. So in other words, the f of the function value at this point AB is bigger than any other function value. That would mean it's a relative max of within a region containing that ordered pair. So it might not be the overall absolute max of the whole thing, but within a smaller subset of the domain, it's a maximum point. F has a relative minimum at an ordered pair AB if the function values at any point xy are bigger than or equal to the function value at that value AB for all points in a region containing AB. So if the value of the function is smaller than any other function value in a region containing AB, we call it a relative min. Okay, so how do you locate those points is the next part. So we use Theorem 1, which is called the D test. Okay, there's a formula for calculating a number D, and based on the value of that number and your partial derivatives, you can determine maxes and mins. If f is a differentiable function of x and y, to find the relative maximum and minimum values of f. Step 1, we find all of our second order partial derivatives. Okay, so we have to find the first partial with respect to x and y, and then the second with respect to x twice, y twice, and then our mixed partial xy. Remember, doing x first and then y versus y first and then x gives you the same number usually, so we'll only do one of those. And then we're going to solve the system of equations by setting our first order partials of x and y to 0. So we set both of our first order partials to 0 and solve that system of equations. So let's say we get a solution. We'll call it the ordered pair AB. Then we're going to evaluate this formula D at our point that we found in step 2. So we take our second partial with respect to x at AB times our second with respect to y twice at AB, subtract the mixed partial x and then y at AB squared. So this is the formula for D. So you should have found all these second partials first. You're plugging in the point you get in step 2 in here. So x twice times y twice minus the square of the mixed partial xy. All right, so then after you've done that, you would know f has a maximum at the point AB if the value of D is positive, greater than 0, and your second partial with respect to x at that point is less than 0. So if you think about second derivative being negative meant concave down, remember that's the upside down like this, like an umbrella, right? That would give you a max. So if D is positive, and that's true for your x sub x twice, right? Concave down, that would be your max. F has a minimum at the point, if again, the value of D has to be positive first, then if your second partial with respect to x twice is greater than 0, remember second partials greater, or second derivatives greater than 0 means concave up in shape, the U would mean you'd have to have a min. F is going to have neither a max nor a min if the value of D is less than 0. Okay, so you only worry about this part if D was greater than 0. If D is less than 0, we don't have a max or a min. We have what we call a saddle point at AB. And if you get the value equal to 0 for D, then you can't use this test. It just basically means it's inconclusive. But a value of D being positive or negative, right, will result in these situations. All right, so let's do an example. Find the relative maximum or minimum values of f of xy equals x squared plus xy plus y squared minus 3x. Okay, first we're going to find all of these partial derivatives. Okay, partial derivative with respect to x is 2x plus y minus 3. Second partial with respect to x would just be 2. And then if I did that second partial with respect to y, or after having done x first, I would get 1. First derivative with respect to y would be, this would be 0. This would be just x plus 2y and 0, so x plus 2y. Then doing it again with respect to y would be 2. And I don't remember, hold on, let's go back here a minute. Remember, I don't have to do y and then x. If I did y, so if this was y and then x again, I get 1 again. But I remember those are typically the same, and I've already done it here. Okay. All right. Solve the system of equations by setting those first partials with respect to x and y equal to 0. So that was my partial with respect to x and my partial with respect to y. The first ones, set those to 0, and we're going to solve this system. Okay, so we can do substitution or elimination. They're doing substitution here. So x would equal negative 2y using the second equation. Then plug that in over here. In place of x, plug in negative 2y. That gives me negative 4y plus y minus 3. That's negative 3y equals 3, so y would be negative 1. Then we can plug that in up here and get x equal 2. So we get x value of 2, y value is negative 1. We call that a critical point. All right, so it's the only critical point we get. Sometimes we get multiple critical points by taking those first partials and solving that system when I set to 0. But here I only get 1, so I only have 1 point to check in my formula for D. Okay, find D. Second with respect to x twice, second with respect to y twice, minus the xy squared, and I'm plugging in this point. Okay, so my second with respect to x twice is 2. If I plug this ordered pair in, take that second derivative with respect to y twice, plug that point in, I get 2 again, minus, and if I plug this, my mixed partial, remember, was just 1 anyway, right? So 1 squared. So I get 3 for the value of D. So it's positive, right? So D is 3, was positive. Then you go back and look at your second derivative with respect to x twice. That was 2, right, which is a positive number. So think of second derivative positive. So D's positive and that's positive. Second derivative positive means concave up, means that you should have a minimum value. So F would have a relative min at the ordered pair 2, negative 1. And the minimum value would be whatever you get if you plug that ordered pair back into the function itself, the original function. So plugging in x is 2 and y is negative 1 back into F and cleaning that up gives me negative 3. So the minimum occurs at the ordered pair 2, negative 1, and the value of the relative minimum is negative 3. All right, so here's another one similar that you could try on your own if you'd like. All right, we're going to find relative max and min of this function. So we're going to find first partial with respect to x, first partial with respect to y, second x, do x twice, y twice, and then the mixed partial xy. So partial derivative with respect to x is 2x plus y minus 7. Partial with respect to y is x plus 4y. And then with respect to x twice, so take that first with respect to x and do x again, we get 2. With respect to y a second time, we get 4. And then the mixed partial, x and then y is 1. So solve the system of equations by setting the first partials equal to 0. So this is the system. So if again we use substitution, you can take the second equation and write it as x equals negative 4y. Plug that in for x into the first one. That gives me negative 8y plus y is negative 7y equals 7, meaning y is negative 1, and then go back and substitute, and we get x equals 4. So the only critical point is, again, 4, negative 1. Find D. That's the formula. These were all constants again. This was a constant 2, 4, and then minus, and then that was 1. So we get 7. So again, D is 7. Second partial with respect to x was 2. So since D is positive, that second derivative with respect to x is also positive, meaning concave up. It would follow that you'd have a relative minimum at your critical point. And then to find the value of the minimum, we plug that back into the original function f to get negative 14. So these are long. These first two examples have been pretty simple, but that's the process. All right, so let's try another one here. Find the relative max and min of this function. All right, so again, start the same way. Find all these partial derivatives. First partial with respect to x, y minus 3x squared. Second with respect to x, negative 6x. And then that derivative with respect to y, second, so x first, then y would be 1. Okay, if I did y first, I get x minus 2y. And if I did that with respect to x, with respect to y a second time, I get negative 2. Okay, now we set our first partials equal to 0. So that was partial with respect to x and y. So here we're going to start with this one this time. You could solve this one for y, then plug it into the other one over here in place of the y. Clean it up. Here you could factor. So this time when you solve, you get 2 x values. Okay, so it's possible to get more than one ordered pair here. So we have an x value of 0 or an x value of 1/6. All right, so we got to find both our y's. So if x were 0, plugging in, or if x were 1/6, plugging into that equation that we had that we substituted. So when x were 0, we get 0, and if x were 1/6, we get 1/12. So we have 2 critical points. We plugged in 0, we got 0, so 0, 0. We plugged in 1/6, then we got 1/12, so 1/6, 1/12. All right, so we have to find D for both critical points. So let's first use the 0, 0. So there's the formula for D again. Okay, so the second with respect to x was negative 6x. We're plugging in the 0 for x. This one was negative 2, and that was 1. So notice here, this is 0 minus the 1, so we get a negative 1. Then we'll do it for the other critical point. Plugging that critical point into our D function. So negative 6 times the x value again. That was the negative 6x was our second partial here, times that derivative second with respect to y twice was just negative 2, and then this one was 1. And we get 1. Right, because this part right here is negative 1 times negative 2 is 2 minus 1. All right, so for the 0, 0 point, the value of D was negative. So when the value of D is negative, I don't care about anything else. That means that that ordered pair has neither a max or a min, but a saddle point. For the other ordered pair, critical point, D was positive. So that's where we have to check the second with respect to x at that point. That was a negative number. That was the first part of the D function, right? That was negative 1. So if the second partial with respect to x is negative, that means concave down, second derivative, max point. So you have a relative maximum at this ordered pair. But this has to happen first before you check that, right? The value of D has to be a positive number. So the value of that max is what you get if you plug that ordered pair into the function f. And if you do that, you should get 1 over 432. So it has a saddle point at 0, 0, and it has a relative max at 1/6, 1/12, and the value of that max is the 1 over 432. All right, so here's another one, similar to the one we just did. All right, so you can try it on your own if you'd like. You can press pause and try it, or you can watch and listen for the explanation. All right, so we're going to start by finding our partials. Partial with respect to x, 3x squared minus 3. Partial with respect to y, 2y minus 4. X twice, 6x. Y twice, 2. And then your mixed partial, if you go back to here and do y, you get 0. Or if you come back to here and do x, you get 0. Either way. All right, solve your system. First partial set to 0. So there was the first partial derivatives. All right, so here, if you started with the first one, solving it, you would get x to be plus or minus 1. So you get 2 x's. We're going to plug that in over here. 2y would equal 4. Well, actually, we can't plug it in, right, because there's no place to plug it. So we just solve for y with the second one. All right, so notice we got 2 x's and 1 y. So we have 1, 2, and negative 1, 2. All right, this one just happened to give me all the x's I needed, and this one gave me all the y's. So again, 2 critical points. So find D for both. Okay, so for the first one, that's the formula for D with the first ordered pair 1, 2 plugged in. So 6 times 2 minus 0 squared. 12. Then for the other one, 6, this one's negative 6 times 2 minus 0 squared. If you go back to your first or your second partial with respect to x, you're plugging in a 1 versus a negative 1. That's the difference. All right, so here we get negative 12. All right, so for the first one, or for the second one, we get D less than 0, right? So we wouldn't even have to check this thing, or no, yeah. So if D is less than 0, your second partial here wouldn't even matter, right? So if D is less than 0, that ordered pair is neither a max or a min, but a saddle point, right? This wouldn't even have to be looked at. All right, for the first ordered pair, D was positive. Here, the second with respect to x was also positive. Remember, second positive means concave up, so that one should be a min. So you have a minimum at the order pair 1, 2. And then to find the min, you plug it back into F and get negative 3. Okay, so here, because D was negative, we could just jump here to say you have a saddle point. Here, because D was positive, that's where you check your second partial to know that it's a min and not a max. All right, so here's an application problem. A firm produces 2 kinds of golf balls, one that sells for $3 and one priced at $2. The total revenue in thousands of dollars from the sale of X thousand balls at $3 each and Y thousand at $2 each is given by this function. R of xy equals 3x plus 2y. The company determines that the total cost in thousands of dollars of producing X thousand of the $3 ball and Y thousand of the $2 is given by this cost function. C of xy equals 2x squared minus 2xy plus y squared minus 9x plus 6y plus 7. All right. How many balls of each type must be produced and sold in order to maximize the profit? Okay, so we have to find our profit function. We were given the revenue function and the cost function. So profit is the revenue, the money you take in, minus your costs. So we take our revenue function, which was this one, and subtract our cost function, make sure that's in parentheses, to get our profit function. So our profit function is negative 2x squared plus 2xy minus y squared plus 12x minus 4y minus 7. So if we're trying to maximize profit, this is the one I have to apply my process to. So I find my partials, all the partials of that profit function that I need. So the first derivative with respect to x, negative 4x plus 2y plus 12. Then with respect to x again, negative 4. And then if I went back to that first with respect to x and differentiate with respect to y, we get 2. First with respect to y, 2x minus 2y or minus 4. And then do that one with respect to y a second time, negative 2. So all my my second partials are constants. All right, solve the system. P of x equals 0, or P sub x and P sub y both equal 0. The first partial set to 0. So there they are. All right, now here, you could do substitution if you wanted to. Here they did addition. So if you go back here, they just said, if you add these, notice if you just add these two equations together, your y's are going to cancel, and that's going to allow you to solve for x. So they're just doing the elimination method instead of the substitution method to solve. So if you add them, you end up getting that because the y's go away. And that allows you to solve for x and get 4. Then you can go back and plug that in to either of those original equations to find your y. All right, so if you plug that into that one, you end up getting the y value 2. So we have a critical point at the point 4, 2. All right, now we're going to find d. So there's our formula for d. The values of our second partials were all constants. Value of d comes out to be 4. So it's positive. So since d is positive, the second partial with respect to x was negative. It follows that you have a relative max, negative second derivative concave down max. So in order to maximize the profit, the company must produce and sell 4,000 of the $3 golf balls and 2,000 of the $2, right? The x and the y. And when they do that, the maximum profit will be P of the 0.42 plugged into the profit function, which is 13 or $13,000. Okay. All right. So the section summary for section 6.3, a two-variable function f has a relative max at AB if f of xy less than or equal to f of AV for all points in the region. And it has a relative min if f of xy is greater than or equal to f of AV for all points in the region. And then more importantly here, that's just more of a general description of the definition, but in practical use to find those points, we use the D test. So we use the D test, the formula for D, to classify a critical point as being a relative max, a relative min, or a saddle point. So that requires finding all your partials, being able to find your critical points, plug them into the D value, and then know what the rules are. All right, so that is the end of section 6.3.